Good afternoon, everybody, and bon après-midi à tous. I would like to express my appreciation and thanks to the organizing committee for the invitation to present my talk on environmental impact of materials, mining, production, use, and recycling. A conference on phosphates is very timely today because society is becoming more environmentally conscious. The world is moving towards an agriculture-based economy as we reduce our dependence on fossil fuels. And without further ado, I will try to share my screen with everybody. And here is the title of my talk. Again, environmental impact of materials, mining, production, use, and recycling. I came up with this particular title because of my interest in plastics. I have been working on polymer processing for 50 years. And in recent memory, plastics have been getting very bad press. Just about every other day or so, I would see something bad on TV, in newspapers, in the social media, hear something on the radio about plastics pollution. Perhaps the bad press has been mitigated a bit because of the recent use of plastics for personal protective equipment, which is all over the place. Masks, gowns, tubing for medical applications for hospitals and everywhere else. So the topic that I'm going to consider, because this is a very, very broad subject, I will focus my attention on three topics: mining of Canada's oil sands, plastic and tire pollution, and natural versus synthetic fabrics. The three topics, they may appear disjointed, but they are not. Actually, they are very interrelated because plastics are really derived from fossil fuels, oil or gas. And a significant portion of plastics, they end up as synthetic fibers, and we have fabrics. And I want to compare those things because my intention is to understand when I hear about plastics pollution, what about other materials? What about mining? And I selected just mining for oil. Now, when you hear mining for oil, you may say, well, production of oil, extraction of oil is really drilling. No, in Canada, it is actually mining. And I'm going to show you how it is done. The problem, of course, comes from the population growth, or I should say, population explosion. In 1930, there were only 2 billion people on this planet. Now we're approaching 8 billion. And if we want to take a look at different regions of the earth, we see that the greatest increase in population is going to happen in Africa, which means that Africa will have the greatest need also for materials. And of course, will have the greatest impact on the environment, which is the subject of my talk today. Well, about oil. The largest proven oil reserves are in Venezuela, Saudi Arabia, and Canada. Venezuela with 301 billion barrels. Proven place with 170 billion barrels. Now, the difficulty of extraction is very different. In Saudi Arabia, extraction of crude oil is easy. It is of good quality, and it's simply drilling. However, in Canada, we don't have that luxury. We have to take oil from oil sands, which is bitumen mixed with sand, with soil, from which the oil must be extracted. This is happening in the province of Alberta in Canada. The area of oil sands, it has been estimated at 142,000 square kilometers, which is larger than the country of my birth, which is Greece, about half the size of Italy. We're talking about a very, very large area. Again, the oil cannot be just drilled. It must be obtained from oil sands. The amount produced by Canada, which is really 97% comes from the Alberta oil sands. There's very little produced by conventional drilling. It's about 3 million barrels per day, which is roughly 3% of the global oil consumption. And here it is, the impact of extracting, of mining for oil in Alberta. As you can see, this is not just impact. I won't call it impact. It is really devastation of the landscape. Now, before this oil exploration, before oil mining, oil sand mining started, there were trees, there were shrubs in this area, but now it is devastation. Now, there are two methods for bitumen extraction in Alberta. One of them is open pit, what you have just seen. Currently, about 47% of the oil is produced by open pit mining and about 53% by in-situ production. Open pit mining is pretty much conventional mining that has little to do with oil, but with other minerals. You know, you have large shovels, you scoop the oil sand, you put it into trucks, you have to crush them, and eventually you have to pump oil into them, separate them, and take them over to the extraction plant. The in-situ production is different, and this is shown here. Now, they drill 2 horizontal oil wells, as you can see, and from the top one, steam is injected. The hot steam is softening the bitumen. The bitumen is converted to a flowable kind of a liquid. It drops to the oil well below, and is taken up by pumps to the surface. And of course, the impact of this kind of technology to the environment is less. It is perhaps only 10% of the open pit mining, but there is an impact as well. After the bitumen has somehow been mined, it has to undergo through some kind of primary sort of processing. We call it upgrading to break down the thick viscous bitumen into lighter, less viscous fluid. The secondary is to remove the impurities such as nitrogen, sulfur, and trace metals so that it can be used for feedstock to refineries. Now, this particular picture shows the processing diagram. I'm not going to say very much or explain too much about it, but if anyone is interested, they can check this particular paper, which has been published in the Canadian Journal of Chemical Engineering in 2004 by Professor Jacob Maslia. But as you can see, it is really the process diagram of a chemical plant. And you can see it better how big it can be. Well, this is one of the plants. All right, by Syncrude, it produces a significant portion of oil in Canada. You see, it's a big chemical plant. I mean, all these dimensions, it's difficult to judge the dimensions, but if it was a person walking around, you would not be able to see it in this particular picture, all right? So it's a chemical plant, and of course, like all chemical plants, they produce pollution, atmospheric pollution, so that the production of Canada's oil also generates a lot of greenhouse gas pollution, which we know that contributes quite a bit into global warming. Well, it's an expensive, of course, operation. I agree with a statement by the economic analyst Nia Williams that Canada's oil sands can survive, but can't thrive in a $50 per barrel oil world. The price of oil, extraction of oil in Saudi Arabia is perhaps around $10. In Canada, we don't really have an exact number, but I anticipate it would be around $35 to $40 per barrel, something like that, or could be even more. But it depends whether it is open pit. Open pit is more expensive. If it is in situ, it is less expensive. But whichever way you look at it, it is an expensive crude oil. And of course, with the current oil prices, which is around $40, you know, it's difficult business to survive in. Well, after the oil has been extracted, the land must be reclaimed and remediated. And the government of Alberta requires 100% land remediation and reclamation. Now, as I said, in situ is substantially less damaging, perhaps only 10% of the damage caused by open pit mining. In the long run, it is expected that 80% of bitumen can only be recovered using in-situ methods because it's too deep in the ground and you really have to drill wells, pump the steam in, and pump the oil out, right? And then subject it to further processing in order to produce crude oil that can be transported to a refinery. Well, there is a picture. An original mining pit at Mildred Lake, Alberta. Obviously, it has been devastated, as you can see. Now, this one has also been fully reclaimed and remediated. Unfortunately, less than 1% of the total area mined has been fully reclaimed thus far. So we have a long way to go. And this situation, of course, has a lot to do with the price of oil. If the price of oil remains at low levels of $40 per barrel or even less, as we have seen in recent months, I do not really know what is really going to happen or who is going to pay for remediation and reclamation. Because with this kind of pricing, some of the companies may even go bankrupt, right? If the prices are low, because this kind of oil extraction, as you can imagine, and as I have told you, is very, very expensive. And this brings me to the next topic of my talk, which is plastics production. Of course, plastics are produced from oil or from natural gas, right? And as I mentioned at the start of my talk, plastics have been getting a lot of bad press, which has been somewhat mitigated by the pandemic due to the ubiquitous personal protective equipment and much more, like hospital gowns, gloves, masks, vials, medical tubing, and so many other things that really create a new kind of pollution. Like we never had so many masks, because what is a mask? You know, you may have a piece of cloth, but inside there is a filter of plastic that prevents viruses or respiratory droplets to go through. In 1945, we had only 1 million tons of plastics produced per year. In 2019, we had 450 million tons per year produced. And from them, only 1 million was biodegradable. This particular slide is from a UN plastic waste report. And it's a very busy picture, as you can see, but it really sort of follows the fate or the cycle of plastics, starting from oil on to production of a monomer, then from the monomer you polymerize, you get a plastic. You can use the plastic, and after its use, you may discard it. Many people do. And if it's not discarded, of course, it can be reused, or it can be recycled by mechanical, by chemical methods, or it can be incinerated for the production of energy. But quite a bit of it also ends up in landfills, right? Now, why do you use so much plastic? Why do we need so much plastic? Well, the average car in 2014 had only 200 kilograms of plastic. In 2020, it is estimated that it will have, the average car, 350, because we try to reduce the weight and we replace the heavy metal with a lighter plastic, right? And the same thing is happening in airliners and all kinds, military planes and everything else. We use a lot of composites. And of course, composites, there's nothing else other than essentially fibers which are held together by plastic. Boeing 777 had only 10% of composites. The new Boeing 787 has 50% of composites. Now, plastics are used in infrastructure projects. Like this one, this is a picture of mine in front of a 2-meter diameter pipe. The same production method can be used up to 3 meters. And such large diameter pipes are used for stormwater or for sewage throughout the world, actually, especially the developing countries where they install new infrastructure projects use much more of this type of technology than the advanced nations that they already had sewer systems and stormwater systems. But the pollution or the plastics pollution that we see is not really happening from the plastics in cars. It's not happening from the plastics in airliners. It is not happening with the plastics of the infrastructure projects. It's happening from plastics used for packaging. And a lot of this packaging is single use. And after a single use, it is discarded, right? As you can see right here, about 36% of the global annual polymer production is for packaging. So we're talking about more than 100 million tons of plastics packaging is produced per year, all right? Perhaps approaching to 200 million tons of packaging, all right? So these are very, very large quantities, and how we deal with them, how we handle them, how we dispose of them, it's very, very important. And now you see, you have probably seen this picture or other pictures like this. And this particular one is from Greenpeace. A lot of plastic is ending up in the oceans. There are millions of tons of plastics circulating. Now, how did we get there in the first place? Why did we allow this to happen, to pollute the beautiful oceans, the beautiful rivers, the beautiful lakes, all right? Let me just take a look. Who are the culprits for this situation? Well, most of the ocean pollution comes from Southeast Asia. China is the bigger producer of plastic ocean debris. Second is Indonesia, Philippines, Vietnam, Sri Lanka. This data were collected in 2010, but the situation has not really changed all that much today. However, there are some other countries that they do extremely well in plastics recycling. Norway does an extremely good job in plastic recycling, with 97% of the plastics bottle for water and soft drinks, they are recycled. Also, India, Japan, and Sweden, they do also very, very well. Many other countries, or most of the other countries, they do not do so well. In fact, some of them, they do very, very badly. There are some innovative systems, like in this small city in Australia, population of 50,000. They invented this kind of a drainage net, which prevents plastics from ending up in the ocean. And hopefully other cities around the world will imitate this kind of technology so we can start reducing the amount of plastic that we discard in ocean waters. Resin identification codes do help in plastics recycling. PET, which is the product, the polymer used for the production of water bottles. And in fact, I have one such a bottle next to me to drink water while I'm speaking. And is the number one, it's the most recyclable plastic. It has a very good price too. The second most recyclable plastic is HDPE, which is polyethylene, high density polyethylene. PVC, it's not as good in recycling, but if it is separated, like if we do not get mixed things up, I think we can do a much better job in recycling, because if we have one bottle of PVC and perhaps 100 bottles of PET, there is going to be big damage to the recycling possibilities of the PET bottles. Unfortunately, in most countries, there is very little plastics waste collection. In separate sort of garbage bins, even in advanced EU capitals, 28 of them, right? On average, only 19% of generated municipal waste is collected separately. 80% of the waste still ends up in the residual waste bin, all of them put together. And of course, once everything is put in the same waste bin, in the same waste basket, right? It's not going to be an easy way to recycle the product. And I can see that from 1950 till 2015, 8.3 billion tons have been produced. 6.3 billion of tons of plastics were generated and have become waste. And they are somewhere where they are. 9% of the waste has been recycled, all right? 12% has been incinerated, and 79% ended up in landfills. Now, in landfills, it's not going to go away. You know, polymers, the success of polymers has been the fact that they're indestructible. They're going to remain there for a very, very long time. We're talking about hundreds of years, perhaps 1,000 years. even if they break down into smaller pieces, like a bottle, let us say, that we throw away and ends up in a landfill, even if we do something to it and we break it down, and it might be broken down due to the conditions in the landfill, the smaller pieces of the plastic will not disappear, will remain there for a very, very long time. We're talking about 1,000 years. Now, for some time, the 3 R's have been introduced as a good way to deal with plastics pollution: reduce, reuse, and recycle. And of course, we have to take another look to biodegradable plastics. Can we develop them? Can we use them? Can they replace the conventional plastics that do not biodegrade? Now, talking about recycling, it can be mechanical, which means collection, separation, cleaning. And you produce then flakes or pellets, remelt them, produce new products. Chemical, you convert them back to monomer. You go through a chemical process and you produce new polymers again. Or the third one is energy recovery, which means that incineration. But of course, incineration is going to produce a lot of greenhouse gas. Mechanical plastics recycling is of great value. You can get very good money with recycled polymer. Like, you can perhaps get half the price of the virgin material, right? But it must be clean. If it is not clean, the price really drops, all right? Here I have some typical sort of prices per ton. And as I say, you can get plastic sort of prices about half of the virgin material. If of good quality, I repeat, if of good quality, which means that the consumer must somehow separate the plastic products. That's why we have the identification codes. And this then can be shipped separately to a buyer, and they do have a good price. And a lot of municipalities, a lot of cities and towns make very good money by selling plastics for recycling purposes. An additional benefit is that with every ton of recycled plastics, we save 2 tons of CO2 because to produce the virgin polymer, we need more CO2 than to simply mechanically recycle the polymer in the first place. Biodegradable plastics. They are mostly starch-based or polylactic acid, PLA, as we call it. They do undergo microbial decomposition to carbon dioxide and water in industrial compost facilities. They usually do not degrade in soil, or very little, to put it that way. So if you have a bottle made out of PLA and you throw it out, it's just going to remain, perhaps not as long as that made from PET or polyester, that is, but it will remain out there for a very, very long time. We need industrial compost facilities to do that. Problems associated with biodegradable polymers. There are some of them. Need collection, composting infrastructure. We must improve their properties because they're not as good as conventional polymers. They also disturb the recycling of fossil-based plastics. They are not compatible, like PLA, which is biodegradable or biocompostable, put it that way. It's not compatible with PET. And if you mix those bottles of the two, you don't have a good outcome. Also, biodegradable plastics require production of corn, or perhaps sugarcane or sugar beets, or other plants, which in turn require the production of fertilizers, herbicides, and pesticides. And I'll come back to fertilizers a bit later, but see, you may think that we solve one problem, right? We went from plastics, which are not biodegradable, to plastics that are biodegradable, but we haven't solved the problem because we have a new pollution problem from fertilizers, from herbicides, and from pesticides. Now, there's also a sustainable alternative to fossil-based gas and oil polymers. Polyethylene is the most widely used plastic today, and it's, of course, produced from oil and gas. But in Brazil, there is industrial scale production from sugarcane. So there is a sustainable solution to the problem. Also polyester, or PET, which is, we talked about, PET, polyester, which we have the water bottles and a lot of fibers that are made from polyester. The benefits versus problems of plant-based polymers. They are renewable. Also, plants absorb carbon dioxide, roughly 2.15 tons of CO2 per ton of polyethylene produced. Well, on the negative side, we have to use very large agricultural land areas, which imply deforestation. And of course, we're going to take away this agricultural land areas from food production, right? There is another kind of impact. And of course, that requires fertilizers, herbicides, and pesticides, as I said. Now, with fertilizers, as you know, and of course, I noticed there are some papers in this conference, fertilizers do cause eutrophication of waters. And the problem is that this eutrophication of waters is really coming from the fact that the significant portion of the fertilizers does not go to the plant, but it is washed away and then ends up in urban waters. Now, for this reason, I think it is absolutely necessary to do more research and more development for controlled release fertilizers. Now, the controlled release fertilizers will not only solve a problem of pollution, reduce pollution, but at the same time, it is very good for the fertilizers industry. For example, in the United States, at least 11 states do not allow phosphates to be used in urban parks or in lawns of various homes, so that by producing controlled release fertilizers, I think we can convince the municipal authorities that these fertilizers really go into the plants. The phosphate goes to feeding the plant rather than ending up in the waters of the city, in a river, in a lake, so that the damage is reduced. By the same time, it's very good for business, as I said. Now, rubber is, of course, is another polymer. And we use anywhere from 1 to 2 billion units per year. Now, what happens to them? They are usually 60% synthetic, 40% natural. The average new passenger tire may be about 12 kilograms. At the end of its life, it's only 9 kilograms, so that we have about 3 kilograms left on the road. And whatever is left on the road, it becomes microplastic pollution, and I'll tell you more about it. But many of those tires that are discarded, they cause some huge fires, as it happened in the United States, and it happened also in Canada. Like in Canada, very close to where I live, there were something like 12 to 14 million tires burning, and the fire department managed to put the fire out in 17 days. Now, like recycled plastic, recycled rubber has a price. If it's again clean and of good quality, the rubber crumb, that is granules, they sell for about $300 per ton. The prices, of course, fluctuate, like with the price of oil and everything else. But from this rather relatively inexpensive rubber crumb, it is possible to obtain rubber again by devulcanizing it. And this is a picture of the process developed by a former PhD student of mine, Kostas Zomerakis, with the injection of supercritical CO2 to swell the rubber crumbs, which is eventually then ends up in the production of new tires. And this is a picture of the plant in nearby Waterloo, and a few other plants have been also built in other places in a couple of other countries. Now, I did mention microplastics. Now, where do they come from? I did mention that microplastics come from tires. And this particular picture, which is rather busy, this is the line right here, which is the percentage of microplastics that come from tire. As you see, in North America, 11.5% of microplastics, they come from tires. They come from whatever is left on the road. However, in India and South Asia, the largest portion of microplastics comes from washing machines. So this is the line for washing machines right here. And the second line is for tires, right? The rest of the contributions and so forth from industrial areas and whatever, they do not contribute very much. But the big culprit right here is washing machines and rubber tires. So we have to do something about them. And this brings me, since I'm talking about washing machines, well, I have to talk about natural fabrics. And of course, you would ask the question that are natural fabrics more eco-friendly than synthetic? You would probably say yes. But are they? That's the question that I want to answer. Now, these are wonderful materials like cotton, linen, silk, wool. On the other hand, we have polyester, nylon. They are more resistant, they are more durable, these products. However, we have to check which has a greater impact to the environment. According to an EU Parliament briefing, natural fibers have the highest environmental impact, with silk especially detrimental effect regarding depletion of natural resources and global warming. Cotton contributing to water scarcity, and wool to greenhouse gas emissions. Linen, on the other hand, is less water damaging, requires less fertilizers and pesticides. But of course, we cannot all use only linen for our clothing, and it's difficult to produce that much. Another question. I did not know about this till I started looking at these issues. According to this UNESCO report, a pair of jeans requires 10,850 liters of water. One cotton t-shirt requires 2,720 liters. I mean, cotton is a wonderful material. It has a great feel. Right now, as I'm speaking, yes, I'm wearing two cotton shirts, an external and an internal one. But I must also be cognizant of the impact to the environment, and of course there are solutions. Maybe we can do some water recycling, we can do certain other things to reduce the impact of cotton to the environment. According again to this EU Parliament briefing, polyester has much lower water footprint than cotton. And a portion of the discarded water bottles and soft drink bottles, 14% of them of the textile market is coming from recycled polyester in 2017, and it is increasing. All right, so that we make clothing from recycled polyester. However, I also have the bad news. One load of laundry of polyester clothes can discharge 700,000 microplastic fibers, which release toxins into the environment and can end up in human food chain. Literally, microplastics can end up into our dinner table. That's why actions have to be taken. I'm not sure what to do about microplastics coming from tires. Perhaps we have to may produce more resistant tires that do not really break down that easily. I haven't heard of any good solution for microplastics coming from tires. However, I see in the international literature different types of inventions, and one of them called coral ball. Apparently, you put it into a load of the washing machine. This will reduce significantly the microplastics. I haven't bought one. I don't really know where to buy it, but I'm going to write after perhaps today or tomorrow. I'm going to write to the company which produces this coral ball and find out how good it is. And with that, I come back to this mantra of the 3 R's, and I have added 2 more R's. That is reduce, reuse, recycle, and redesign and research. This is what I'm adding. We must redesign many of the products that we use. Perhaps we may have to redesign tires, but not only just tires, but perhaps we have to redesign our lifestyle. For example, in North America, wherever you want to go, there's only one way to go. You have to have your private car or jet plane. There's very little public transportation. Train is not really used. Buses, they are used buses, but it's mostly private car or jet plane. This is so that whereas in Europe or Japan, for example, public transportation is much better. Now, another thing we can do is research for better methods of recycling, research for biodegradable plastics with better properties, and research certainly for fertilizers that will not pollute urban waters, perhaps control release fertilizers that will contribute quite a bit to reduction of water pollution. And with that, I'd like to thank you. And I would now stop screen sharing and go back to my computer, and I will ask you if you have any questions. Thank you.